Okay, we're gonna have our last online exam this Friday, exam 3A. So please, don't forget that. It's like a quiz. It will be open between 2 and 11:59 p.m. You get two attempts, and highest attempt will be taken. So you know the drill. So this is going to be the last one. All right. Just keep that in mind. Apart from that, I've already opened discussion worksheets for next exam and the homework assignments and stuff like that. They are available. So when you have time, just work on them. That's all you need to do. You don't need to do anything else. But work. I mean, if you can work on the questions I provide with, I have provided already. It should be enough for you to get an A in this class. All right. What questions, concerns, comments do we have at this moment? Anything? Any questions, concerns, comments? All right, if that is the case, let's start with discussion on the screen. Chemical formula is C2H2Cl2. Draw all the possible isomers for this. What are isomers? I have defined that in the question itself. All right, they have the same chemical formula but different spatial arrangements of the atoms. Okay, and then determine which one of these isomers are polar. All right. So before I look at your answers, I'm going to draw them in my notebook. Okay. So you were given the formula, which was C2, H2, Cl2. Okay. So the possible structures are you can have something like this. We need to have a carbon double bonded to two carbons double bonded to each other. Otherwise, it won't work. Okay. And then the options are we can have the two Cls on the same side, like this, and then hydrogens here. Or you can have the two Cls on either side. Okay. Say one of them up, the other one down, and then the hydrogen. Okay. Or you can have the two Cls bonded to the same carbon like this. So Cl and Cl and hydrogen, hydrogen. So these are the only possible structures for this chemical formula. I mean, if you want to make them Lewis structures, you know that you need to have the lone pairs. Otherwise, it's not a Lewis structure. That's the goal. Okay. So do we have any questions, concerns, comments about that? Anything? Okay, these are the only possible structures. And also, I'm going to show you the line structures as well because I like line structures. They're easy to draw. So for the first, oh, by the way, yeah, you know what? I'll draw line structures. For the first one, I can draw it like this. Okay, we have the double bond, and then we have the two Cls on the same side. And then for this, we have the double bond. We have the two Cls on either side. And then for this, we have the double bond. And then we have the two Cls bonded to one of the carbons like that. That's it. Line structures. Okay. And there's one other thing I want to mention here. Not that I'm going to go after names of these. Okay, I couldn't care less about names. Okay. But here, when we have the two chlorines on the same side, okay, for any other major groups for that matter on the same side, if they're on the same side, that conformation is known as cis isomer. If you have them on either side, like one up, one down, like that, okay, so they are known as trans isomers. Okay, and for this, there's another name as well. I can't remember it now, but it doesn't matter. So you will mainly come across cis and trans isomers. Okay, maybe on labels, maybe on your margarine or butter or whatever you consume. You might say that we have cis or trans fatty acids. Okay, that is what we mean. All right. So, what questions, concerns, comments do we have up to this point? Anything? Any questions, concerns, comments? Okay. So now Sophia, can I borrow that red pen if you don't mind? Okay. Now the question was, which one of these are polar? All right. And how do we determine that? So you know that if we have like cis isomer like this, okay, you have two bond dipole moments going in this direction. Here's one, here's two. The arrowhead is towards chlorine. Why? Chlorine is the most electronegative atom. Therefore, if you add them up, you will see that the net dipole moment should be in between the two chlorines. Okay, like this. So this is the net dipole moment of this molecule. When it comes to trans, you have a bond dipole moment going this way, another one going the opposite way with the same magnitude. Okay, when you add them up, they cancel each other out. Therefore, the net dipole moment is 0. On the other hand, for the last isomer over here, we have two bond dipole moments going towards right, based based on the way you draw it. It could have been on the other side as well. But we know, therefore, the net dipole moment should be going towards the two chlorines like this, okay, in the direction of the two chlorines. So we have two polar isomers. Unit will be not 0 here. So these are my polar isomers out of the 3 possible isomers. All right. What questions, concerns, comments do we have at this moment? Anything? Any questions, concerns, comments? Okay. So, by the way, I want to mention another thing here, just for clarification. These are not resonance structures. Okay. So the difference is in resonance structures, the spatial arrangement of the atoms do not change. They are going to be in the same position, but the double bond is changing. The electrons are changing, are moving around in resonance. But in isomers, you see that they have the same chemical formula, but the spatial arrangement of the atoms are different. In cis, you have the two chlorines on the same side. In trans, you have the two chlorines on either side. And in the other isomer, we have the two chlorines bonded to the same atom. It can be chlorines, it can be some other groups, but you know, the idea is the same. Okay. All right. Any questions, concerns, comments at this moment? Anything? Any questions? Okay. So now we know this. I want to point out one other thing, and I want to get back to this. Okay. The other thing I want to mention before we start the new module is this. If you have molecules that contains only hydrogen and carbon, they're also known as hydrocarbon molecules. Okay, they are considered non-polar molecules for all intents and purposes. Okay, for all government work, okay, they're considered as non-polar molecules. Okay, one more time. If your molecule contains only hydrogen and carbon, or in other words, if you have a hydrocarbon molecule, they are considered as non-polar molecules for all intents and purposes. All right. Okay. Remember that. All right. Do we have any questions, concerns, comments at this moment? All right. If that is the case, this is what I want you to do. I want you to go back to what we drew on our notebooks. Okay. So let's take the cis isomer, which is a polar isomer, right? It looks like this. Okay. Can you show me how two polar isomers, like cis isomer in this case, would interact with each other? Go ahead. How do you visualize, or how do you envision these molecules interact with each other? Go ahead. Yeah, you have drawn the structures, which is wonderful. Some of you drew it right away. Some of you get in there. That's okay. So anyway, if somebody twisted my arm and asked me to draw, like how would these molecules interact with each other, I would do this. Okay. So now we know these molecules have a dipole. Right? So dipole means you have a net dipole moment. So a dipole, when I say dipole, I'm talking about this net dipole moment. All right, this is what is meant by a dipole. Okay, so let's say that this is one of these dipoles. Okay, and then if this dipole interact with another dipole, okay, would this head of this dipole interact with the head of the other dipole or the tail of the other dipole? It should be the tail, right? Thank you. Why? We know head is partially negative and the tail is partially positive. Opposite charges are attracted to each other. Therefore, head of one dipole should interact with the tail of the other dipole. So it should look something like this. Okay. Why this is the case? Because we know tail is positive, head is negative. They would like to come closer to each other. They are attracted to each other. Okay, so this is going to be how it looks. Okay, now what I'm going to do is I'm going to draw the molecule on top of this. I know that if I draw this molecule on top of that, it should look something like this. So here are my chlorines, and then for the same thing here, right, my chlorine atoms. Right, so this is how I would draw them. Okay, I would not draw them like this. Okay, Cl, 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 Cl. Right. Why wouldn't I draw it like this? Anybody? Come there again. Thank you. They're going to repel each other, right? So in this case, two heads are coming closer to each other. You know, they are not going to be attracted to each other. They are going to hate each other. They are going to repel each other. Okay. As a result of that, this is not possible. All right. The same thing. And also, if somebody drew like this, all right, that is not possible either. Right? Because if you draw like this, you know, tails are trying to interact with each other. Tails have the same charges. Okay, they will repel each other. They won't be attracted to each other. Therefore, this is not a possibility as well. So this is how they would interact with each other. Okay. Now, so when they interact with each other like that, they are known as intermolecular forces. Okay, this is the idea of intermolecular forces. There are 3 types we are going to learn this semester for intermolecular forces, and we have to name this. So we have one dipole interacting with another dipole. Okay, dipole interacting with a dipole. Okay, dipole, dipole. What can we call these interactions? Anybody? Any name? Come there again? Thank you. We call them dipole-dipole forces. Not that creative, I'm sorry, okay? But that works, okay? These interactions are called dipole-dipole forces. Dipole-dipole forces. You know why, right? Because 2 dipoles interact with each other head to tail. All right, that's the first intermolecular forces we learned today, okay? Dipole-dipole forces. What questions, concerns, comments do we have? We are officially in Unit 3, Module 1. This is the segue to Unit 3, Module 1. Interactions between molecules. Did we have a question somewhere, Fani? Did you say somebody? Yes, sir. Can I have the microphone there, please, Ashini?
So for that was for one structure of like the polar dipole. Could you do it for the other one as well, like where the arrow's pointing to the side?
Yeah, it's the same thing.
Same thing. Okay.
Yeah, same thing. Yeah. So yeah, exactly. You can do the same thing for the other one as well. Again, if somebody asks you to draw dipole forces, they are very easy. All you have to do is draw one dipole kissing the head of one dipole kissing the tail of the other dipole. Okay, this happens all the time in dog parks, right? Anyway, same thing. Now, if you have to use this isomer instead, so what you need to do is, so you draw the molecule over it like this. Here we go. Yeah. So this is another way. This is how 2 of the other isomers would interact with each other. All right. What other questions, concerns, comments do we have? Anything? All right. Now, here's what we're going to write actually. So we can actually generalize intermolecular forces. Now, get this really straight now. Okay. Intermolecular forces. Let me write that. Okay. Intermolecular forces. Okay. In short, IMFs. Okay. Intermolecular forces are due to get this attractive interactions between opposite partial charges of molecules. Okay. In other words, for you to have intermolecular forces, you need partial charges. Okay. So when you have opposite partial charges, they are going to be attracted to each other. That's the idea there. All right. What questions, concerns, comments do we have? Anything? Any questions at this point? Okay. All right. So if that is the case, let's remind us about what we already know about intermolecular forces. Okay. So, right, just to remind us about where we are at now. Okay, what we have done so far and where we are at. So we learned how to determine the composition of molecules using mass spectrometry and elemental analysis. And then in unit 2, module 3, we learned how to draw the molecules, the Lewis structures of the molecules, and to the correct geometry. Okay. And then in unit 2, module 4, we knew how to assign partial charges and to decide whether they are polar or non-polar molecules. And then you know that when they interact with each other, opposite partial charges, like red area means you have a high electron density, blue area means you have a low electron density. So that means a partial positive charge. Okay, that means they are attracted to each other. So these are the intermolecular forces. And due to this, we have what we call emergent properties or macromolecular properties that we can explain, like density, viscosity, melting point, solubility and stuff like that can be explained using intermolecular forces, as we have seen in unit 1, module 1. Okay. Now, what I want you to do is I want you to think back to unit 1, module 1, or module 2 maybe, right? And answer this question. Go ahead. Questions about viscosity again. All right. If you take honey and water, honey is more viscous than water. It's called the resistance to flow. Okay. So thickness. So say that honey is more thick, or honey is thicker than water. All right. I think that should be enough time for discussion. We have more than 90% answers. Therefore, I'm going to close this question in 5, 4, 3, 2, and 1. So just to remind us, if you go back to our notebook, okay, in a previous life, go back, okay, we actually talked about this directly. I think we did, at least. Oh, here we go. Right? The stronger the intermolecular forces, higher the boiling point, higher the melting point, higher the density, higher the viscosity, lower the volatility, lower the vapor pressure. Okay, this should be in our notes already. Okay, if you don't, I mean immense. All right. So if that is the case, think about this now. Okay, so between oxygen O2 and N2, which you find in the air we breathe, I'm going to ask you a question actually. Okay, can you let me know which one has a higher boiling point? You can Google or chat GPT or use any AI. Okay, which one has a higher boiling point, oxygen or nitrogen? Go ahead. Oxygen is O2, nitrogen is N2. Okay. Which one, help me, out of nitrogen and oxygen, which one has a higher boiling point? All right. Can I see your whiteboards, everybody? So we see between oxygen and nitrogen, I see O2. Oh, nitrogen, O2, O2, nitrogen, oxygen. Yeah, these are option, right? Nitrogen and oxygen. Which one is it? Oxygen. All right. So if your AI tells you it's nitrogen, oh my goodness, get rid of that. Get a better one. All right. So between nitrogen and oxygen, oxygen has a higher boiling point. All right. So you should, stick with standard Google if you have another answer there. All right. So that means molecules. Everybody, thank you. We have strong intermolecular forces between oxygen molecules. Okay, that's why it has a higher boiling point. Now, here's the question for you. Now, what are these intermolecular forces? Right? Can you draw them out for me? Go ahead. You might want to check what we wrote about intermolecular forces about 5 minutes ago in our notes. Intermolecular forces are due to that. And then oxygen has a higher boiling point, therefore it should have strong intermolecular forces. Oxygen or nitrogen for that matter, okay? Is it polar or non-polar? Thank you, it's a non-polar molecule, right? Therefore, do they have partial charges? Do they have partial charges if it is non-polar? No. Actually, to be more technically correct, they do not have, get this, permanent partial charges. Okay? Yeah, they can have, I heard that term, induced partial charges. So what is meant by that? All right, we'll talk about this. All right? So it has to do with this idea called polarizability. Okay? So what it means is, I mean, as the name implies, okay, ability to be polarized is called the polarizability, meaning ability to have partial charges. It's called polarizability, right? So here's the thing that you need to know. Anything with electrons, basically everything that you come across in your life, okay? It can be an atom, molecule, ion, polar molecule, non-polar molecule, a hair, chair, pen, I don't know, anything that you come across in your life will have electrons, okay? Therefore, they are polarizable. Okay, that's one thing to appreciate. Okay, now just for the sake of sake of completion of our notes, let's write this down as well because we are coming across this term, right? So polarizability, polarizability. Okay, what is that? Polarizability is the ability to be polarized. Very simple. Okay, or polarized, or have uh, induced partial charges. Within parentheses, I'm going to write have induced partial charges. I need to zoom in. I know. I'm sorry. Oh, that's zooming out. That's zooming in. Is this way. Here we go. Okay. So polarizability is the ability to be polarized, meaning to ability to have induced partial charges. Okay. And along the same lines, I want to write, because we want to know this, because this is the most important thing that you learn today, by the way. Anything with electron, anything with electrons, or electron clouds, or electrons, is polarizable. Oh, polarizable. Okay. We want to make sure that we know that. Anything that you can think of is polarizable. Why? They have electrons. All right. Now, how does it work? Let me show you a simulation. All right. So let's think about an innocent atom minding its own business like this. Okay, like maybe a hydrogen, I mean, maybe like neon or argon or helium or something like that. Okay, so it is minding its own business, meaning it's going to have a nice spherical electron cloud. Okay, what you're going to do is you are going to introduce a charge nearby. All right, let's say that on the right hand side, you introduce a charge, a negative charge, okay, like this. Okay, what happened to the electron cloud of this atom? What happened to it? Can you please make an observation? What happened to the electron cloud? One more time, I'm going to do it. I want you to do this, okay? So this is when I don't have a charge. We have a nice spherical electron cloud. But when I bring a charge nearby, like the negative charge, what happened to the electron cloud? I want you to come up with a word. Can you come up with a word? Write it on your whiteboard. Okay? Because I brought a charge nearby, the electron cloud of this nice spherical atom. Okay? I got one word. I like to see these words actually. Smoothed. I like it. What else? Shifted. What else? Shifted. What else? I mean, I want you to come up with something, not a boring word like shifting. Can we have a little bit more exciting word than shifting?
Push your board up.
But boot? Okay. That's too Halloweeny. No. All right. All right. Thank you. Shifting. Okay. All right. You guys are boring people. All right. I got overlyzed. Oh, like that. Okay. Repelled. Stretch. Repel. Okay. Okay. All right. Can I say it? Transferred. Okay. To one side. Okay. Okay. All right. So here's the word I use. Okay. So squish. Okay. I like it. I saw this. Smooshed and squished. Okay. All right. Thank you. So here's the word I use. Because of this external charge, the electron cloud got perturbed. Take that for a word. Okay? Got perturbed. All right? Meaning disturbed. It got disturbed or perturbed. Okay? Do you want me to write it down? All right. Okay, look it up. Maybe I'm making this up. So you know what? Just go to Google. Google. Okay? Perturbation. All right? It's going to deviate or, moving object or anyway, whatever. All right? So that's the term I'm going to be using. Oh, where's my notebook? Here we go. All right. Let me write the word so that everybody's on the same page. Okay. Perturbed. Okay. Anyway, so as a result of that, now here's what happened with this, right? This is the most important thing. So because of this perturbation of the electron cloud, one side has a higher electron density. If that is the case, what will be the partial charge on that side? Thank you. Partially negative. Very good. All right. So this side with more electrons will be partially negative. On the other side, it is exposing its nucleus. Nucleus is positively charged as well, right? So what will be the charge on the other side then? Thank you. It should be partially positive. There you go. We just induced partial charges on we are sitting somewhere and somebody comes closer and gets us perturbed. Sometimes in a good way, sometimes in a bad way. Right? Anyway, same things happen with the electrons or the particles, atoms as well, or molecules as well. Okay, molecules, I mean, they might be minding their own business. Just because somebody else come closer to it, it can get perturbed. As a result of that, they're going to start interacting with those molecules. Okay, so that's the case. All right. Now, this is the idea of induced partial charges. Now, when we have induced partial charges, or we also call this induced thank you, Robert. Induced dipole moments. Okay. Now, these induced dipole moments can interact with induced dipole moments. Right? So, for an example, let me show you oxygen now. So, here's one oxygen molecule. I'm not going to draw anything else, okay? And then here's this electron cloud, okay? And then here's another oxygen molecule over here, okay? And this is this electron cloud. When they come closer to each other, they perturb each other's electron clouds. As a result of that, they are going to induce partial charges on them. So it's going to be partially this is random, partially negative, partially positive. They can interact with each other. Here's partially positive and partially negative. They can interact with each other. Okay. And these interactions are called, does anybody know the name for this? Okay. We'll get there in a bit, Williams, but you are not incorrect. But, okay, these are interactions between induced dipoles. So these are known as induced dipole, induced dipole forces. That's too long, right? Anyway, so but that makes sense because we induce a dipole, and now this induced dipole interacts with each other. Those are known as induced dipole forces. Okay, they are also known as London forces, London dispersion forces. Okay, also known as, what did you say, William? Okay, van der Waals forces. Van der Waals forces, also known as dispersion forces. Oh, I zip gun. Okay, dispersion forces or London dispersion forces, whatever. Okay, so in our class, we are going to refer to these intermolecular forces as dispersion forces. That's the name we'll be using. All right. What questions, concerns, comments do we have at this moment? Right. So there are three types of intermolecular forces. We learned two of them. Out of the three, when you are learning for the first time, dispersion forces is the weirdest one. All the others are very straightforward. Okay. Okay. I mean, once we get this down, it's going to be downhill. It's going to be much easier for us. All right. Any questions, concerns, comments at this moment? Anything? All right. Now, what I want you to do now is, let's think about what polarizability depends on. Okay. Right. Let's do this. So let's say that you, okay. Right. And that's the correct answer as well. Why? Can somebody tell me why? Why did you select that? William, go ahead. Can I have the mic? Okay, take a second, William. All right. William, what say you?
We chose 2 because there's a bigger electron cloud, meaning there's a larger chance for a temporary dipole to form.
Thank you. Okay. When you have more electrons and when it is larger, you have more opportunities to be polarized. Okay. So for that reason, it is going to be more polarizable. Okay. So just to summarize the learning from that activity, polarizability will be greater with more electrons over a larger volume or a more surface area of contact. Okay. So with more electrons and then larger size means more polarizable. That's it. Okay. That's the one you should have in your notes. Okay. Larger molecules with more electrons are more polarizable. If you can have that in your notes, that would be wonderful. All right. Now, I'm going to actually, do this in my notes as well. At least, I expect you to write everything I write in my notes, in your notes too. Okay. So, one more time, polarizability is directly proportional to, this is the proportionality sign, to the number of, this is the number, pound sign is for number, okay, hashtag electrons, okay, number of electrons, okay, and size, okay. Higher the number of electrons, higher the size, higher the number of electrons, greater the polarizability, okay. Larger the size, greater the polarizability. That's it. Okay. All right. So remember one other thing. When I say number of electrons here, I refer to the total number of electrons, not just the valence electrons, but the total number of electrons. So we're going to learn how to count these in the next activity. Okay. So let's try this. Here are 3 molecules. I want you to count the total number of electrons in these molecules. Go ahead. All right. Compared to the people who did not count the number of electrons. Okay. Because you're going to make mistakes, like you're going to count the valence electrons first, and then we're going to figure out that's wrong. So we need to find the total number of electrons, and that's the learning process. Okay. You won't have that opportunity if you don't do that. All right. Anyway, so we have close to 90% answers now, meaning I'm going to close this question in 5, 4, 3, 2, and 1. All right. And here are our responses, which is pretty good. All right. But the trick is to being able to count this. All right. And how do we get 42 electrons in CF4? Carbon atomic number is 6, meaning it has a total of 6 electrons. So with carbon, we get 6 electrons. Okay. Plus, we have 4 fluorines. Okay. What's the atomic number of fluorine? 9, right? That means fluorine has 9 electrons. So 4 times 9. 4 times 9 is 36. 36 plus 6 is 42. And that's how we get 42 there. Okay. I'll do one more. CCl4. Carbon is 6. That's the atomic number of carbon. Therefore, it's going to have 6 electrons. We have 4 chlorine atoms. Each fluorine has 17 electrons in it. How do we know it? The atomic number of chlorine, according to the periodic table, is 17, meaning it has 17 protons. If it has 17 protons, it should have 17 electrons as well. Okay. So, and then we have 4 times 17, right? And then 4 times 17 is what? 60, it should be 68, right? Yeah, 68 plus 6 is 74. That's how we get 74 electrons in CCl4. All right. What questions, concerns, comments do we have at this moment in counting total number of electrons? Anything? Okay. So if that is the case, now we know that. Now we'll arrange the same molecules in the order of increasing polarizability. Let's get there. Here we go. Answers. So let's see how we did. And here are our responses. Most of us said CF4 is the least polarizable because it has the least number of electrons, and CBr4 is the most polarizable because it has the most number of electrons. And then that's the correct answer as well. 95%. I cannot get better than that. Wonderful. All right. So we know the polarizability and then what polarizability depends on. Wonderful. Now, here's the last piece of the puzzle. Okay. Let's think about the connection between polarizability and dispersion forces. Okay. So if you have like less polarizable molecule, like this one over here, okay, yeah, you will have some partial charges and then some opportunities to interact, for them to interact with each other. But if you have a more polarizable molecule, meaning with a molecule with more electrons and then a larger molecule like this, you have more partial charges and more opportunities to interact with each other. As a result of that, if you have a more polarizable molecule, what can you tell me about the dispersion force strength? Will it be stronger or weaker? Everybody. Thank you. It should be stronger. Why? You have more opportunities to interact, more partial charges to interact with. Therefore, greater the polarizability, stronger the dispersion forces. Right? Greater the polarizability, stronger the dispersion forces. That's it. All right. Now we're gonna make that note. I'm gonna do that for you. Okay, we're gonna do this together. Okay. Where should I do it? All right. Let's do this together. Okay. So there are three types of intermolecular forces. We already know this. All right. So we have dispersion forces. Right? We have dipole forces. We talked about that already. Okay. And the third type is, the third and last type is, does anybody know what's the other type of intermolecular forces, which we haven't talked about yet, but which we will? Thank you. It's called hydrogen bonding forces. H bonding forces. This is it. H bonding forces. Okay. So we learned the dispersion force strength depends on polarizability. Okay. Greater the polarizability, stronger the dispersion forces. And we also know polarizability depends on the number of electrons and size. Okay. And then for the completion of our notes, I'll write about this dipole forces as well. Just like dispersion forces depends on the polarizability, dipole forces depends on the molecular polarity. Molecular polarity or net dipole moment. Higher the molecular polarity or higher the net dipole moment, stronger the dipole forces. Okay. And when it comes to hydrogen bonding forces, hydrogen bonding force strength depends on the number of hydrogen bonding sites. We haven't talked about what hydrogen bonding forces are yet. They're very specific, but they're very easy to remember as well. But we'll talk about it in a second. But I mean, on Thursday. Okay. But these are the only three types of intermolecular forces that we need to be concerned with: dispersion, dipole, and hydrogen bonding. Okay. By the way, I'm organizing your notes for you. You should have at least something like this in your notes. All right. What questions, concerns, comments do we have at this moment? Anything? All right. If that is the case, now let's put this into practice. All right. Same molecules first. Here we go. Arrange the same molecules that we dealt with before from weakest to strongest dispersion forces. Weakest at the top, strongest at the bottom. Go ahead. Question. I like it. All right. So we have more than 90% answers. Therefore, I am going to close this question in 5, 4, 3, 2, and 1. All right. And here are our responses. The most popular order is CF4 will have the weakest dispersion forces and CBr4 will have the strongest. That's the correct answer as well. 93% of us are there already, which is wonderful. All right. Do we have any questions, concerns, comments at this moment? All right. Let's keep practicing dispersion forces for now. Here's another question for you on your whiteboards first. Actually, Yeah, I made a little boo boo here. When I made the top hat question, I replaced neon with argon. It's gonna change something, but it's okay. Actually, we should do the top hat. Maybe we can do the top hat question. But the ideas are the same, okay? I mean, if you know how to do neon, we know how to do argon as well. It's the same exact thing. Yeah, you're predicting the boiling points, okay? Relative boiling points. That's what you're doing. And yeah, let's do this on top hat. All right. So before I look at your answers, I'm going to show you the way I would think about this, okay? First thing, if we have to predict relative boiling points, okay, even though we do not know what is more important, whether it is number of electrons or size, we need to start somewhere. Therefore, we will start with number of electrons, okay? So helium is atomic number 2. It has 2 electrons. And CH4 has 10 electrons. Carbon 6 and 4 electrons from the 4 hydrogens. And then argon has 18 electrons because its atomic number is 18. And C2H6 has 18 electrons as well. Okay, how do we know it has 18? Carbon has 6. We have 2 of them, 2 times 6. Okay, plus 6 times 1 from the 6 hydrogens. So 12 plus 6 is 18. All right. So because you have most electrons in argon and C2H6, they should be the most polarizable. Therefore, they should have the strongest dispersion forces, meaning highest boiling point. And then CH4, and the least polarizable is helium. Therefore, it should have the weakest dispersion forces, meaning lowest boiling point. Between argon and C2H6, C2H6 is a larger molecule because we have 2 atoms bonded to each other. On top of that, we have hydrogens sticking out from each carbon, like 3 of them in each case. Okay, because it is a larger molecule larger particle than argon, they are, even though they have the same number of electrons, it should be more polarizable. Therefore, you have stronger dispersion forces in C2H6, meaning higher boiling point. Okay, so that should be your order. All right, now just to summarize, I'm going to show you the actual boiling points of the previous question as well. Okay. Oh, sorry. Here we go. So these are the electron counts and the boiling points of the previous question. Okay, so it works. Okay, so these are all nonpolar molecules. Only dispersion forces are at play, and this is how we decide that. All right, so with that, I'm going to give you your attendance code. And when we come back on Thursday, we will work with dipole forces and also hydrogen bonding forces. Then we're done with first part of Unit 3, Module 1. All right, bye everybody. I'll see you Thursday.